Hi, we're going to do a little bit of revision on radioactivity today and specifically half-life. So the first thing I want you to think about is what is the smallest number in the world? Now what lots of people might think is that negative numbers are very, very small. But negative numbers are not small. Minus 10 is still a negative number, and minus 11 is a bigger negative number because the magnitude of the number is getting bigger. So like minus infinity is a big number, it's just a negative big number. So actually the smallest numbers in the world are when you get close to 0. So as you can see here, these numbers are halving every time. So 1, half, 4, 8, 16, 32, 64. Okay, so the smallest numbers of the world are as you're approaching to 0. Now in the world around us, we have background radiation. Now you don't need to know these percentages, but you do need to know what background radiation is made up of. So background radiation is made up of mostly radon gas from the ground, okay, which is an alpha emitter. We also get gamma rays from grounds and buildings. So the materials inside the ground that's then dug up and made into buildings is radioactive and can produce gamma rays. Okay, so that's where some of it's medical, so we use it in hospitals we use it for PET scanning, and we use it for radiation therapy for cancer. We also have some from the nuclear industry, so we use the products of nuclear power are radioactive. We also get some cosmic rays. They're rays from the sun, so basically gamma rays from the sun. And then we have 9.5% for food or drink. Because food and the things that go to make food and the things that go to make drink are grown in the ground, and the ground contains radioactive material, when the creatures and the plants grow, they then contain radioactive material as well. And remember, when we're talking about radioactive material, we're talking about things that emit gamma, beta, and alpha. Okay? So, half-life. Now you might have done the practical with the dice where you threw a dice and you removed the dice every time it showed a number 1 or a number, no, I think it was just a number 1 initially. And when you plot a graph of that, of throw number against number of dice left, you get this curve. Now this looks like a radioactive half-life curve. So if you want to work out how long it takes for the number of dice to fall by half, you count the number of dice you've got at the start, halve it, draw a line across, and then down, and then take your throw number from there. What you can then do is halve this number here on the side again. So let me just say, if this was 30 here, oh no, that's not going to be a nice number. Let's go for 32. So we've got 32 dice left. Half of 32 is 16. Okay, and let's say that took 3 flows to get from 32 to 16. If I then halve, oh no, it's gone. Oh no, hang on a minute. Let me just write that again. So we've got 32 here. We halved it to 16 and that took 3 throws. If we halve 16, that's 8, and that should take another 3 throws, so that should happen on number 6. So if this was a half-life graph, we'd be saying our half-life is 3 throws. Okay, it's the number of throws it takes for the number on the left-hand side to halve. But in radioactive decay, it's not number of dice left, it's number of undecayed nuclei left, okay? So, let's have a look what's happening there then. So the decay of radioisotopes can be used to measure the material's age. The half-life of a radioisotope is the time it takes for half the nuclei in a sample to decay. So, the black ones here, they're the ones that are radioactive. So they haven't necessarily given out their radioactivity yet, but they have the potential to. Because with a radioactive sample, all the atoms don't give it out, all their radioactivity out at once. It's like some of them will give it out some of the time. So for example, if you think about popcorn, if you put popcorn in the microwave, all the popcorn kernels don't pop at once. What happens is that they will pop randomly at different times. And once they've popped, they can no longer pop again. That's exactly the same as radioactivity. So a radioactive isotope will give out radiation randomly at some point, okay? And once it's given it out, it's now a new material. And so you would have to then look at it separately from the original isotopes. So these are your original radioisotopes, they're black, and then they make these new red atoms. So initially here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 radioactive isotopes. So at time 0 there are 16 radioactive isotopes. After a half-life, half of the radioactive isotopes will have given out their radiation and turned into a new atom. So look, 1, 2, 3, 4, 5, 6, 7, 8. So 8 of them have turned into a new radioactive isotope, and the original ones are still there and they have not changed yet. So after one half-life, half of them have decayed. Now, after another half-life, you need to look at how many black ones are left, and half of those will decay. So 1, 2, 3, 4, 5, 6, 7, 8. So after another half-life, 4 of them will have decayed. So we've got 4 left, and now we've got the original 8 from here, and then another 4. So 12. Okay. And then we've got 4 left, so after another half-life, 2 more of these will go. So 14 of them will have changed, and you've got 2 left. And then after another half-life, 1 more would go. Okay, so every time you're counting the number that are left and halving it. So we use that for something called carbon dating. So there's a radioactive isotope called carbon-14. It's around us all the time, and it pretty much stays in living material at a constant level. So carbon-14, when you're alive, because you're breathing it in and out and taking in the same amount as you give out, it remains constant. As soon as living material dies, so let's say a cow for making leather, or maybe a human being a mummy, or maybe it might be a plant that's being used for something. As soon as it dies, the carbon-14 levels start to go down because you're not taking the same amount in as you're giving out. Now it has a half-life of 5,700 years. So living material has a predictable amount of carbon-14 in it, as I've just talked about. And then when living material dies, it begins to decay with a half-life of 5,700 years. So let's say there's a dead cow, okay, and you go to make a belt, or you find a belt, okay, a leather belt. So let's say here's the cow, it's died, someone makes a leather belt out of it, and that leather belt contains 10 grams of carbon-14. It then starts to decay. It gets buried, okay. After 5,700 years, that is its half-life. So instead of having 10 grams of carbon-14, half of it would have decayed, so it would now contain 5 grams. After another 5,700 years, you've only got 5 grams of carbon-14, so that halves, and now you have 2.5 grams of carbon-14. So if someone comes along and digs up your belt and says, oh, well, if this belt was new, it would have 10 grams, but it's only got 2.5. I know it's been through 2 half-lives. So it's gone from 5 and then to 2.5. So they can say, well, I know that that is going to be 2 half-lives of age. So that's going to be 5,700 plus 5,700, which is 11,400 years old. So you can use that for carbon dating. Okay, I'm going to go through some questions showing you how to do half-life calculations and things, but you can obviously make notes from this PowerPoint initially.